Okay, sorry, I didn't know the last one cut off. So I'm gonna back up for just a minute. Um, okay, so we're talking about these melting points over here. And ionic compounds are like held together really, really, really tight. So it takes so much energy to break them apart. That's why their melting points are so high. So if you get a question that's like rank this based on melting point or boiling point, think about it. To melt something, you have to take it from solid, where it's really compact and all together, right? And you have to turn it into like this fluid liquid. So you have to separate the particles. We talked about the space to particles. And then to boiling, we have to put a lot of space between our particles, right? So you've got to separate the particles. If they're held together really tightly, like ionic bonds or hydrogen bonds, they're going to have a lot higher melting and boiling points. If they're held together really loosely, like dispersion forces, they're going to have really low melting and boiling points. So you can tell a lot about something based on its polarity and based on its intermolecular forces or the attractive forces. How do you know if something's polar? You have to draw it out, right? You have to be able to see like, okay, what kind of shape is it? Are the dipoles canceling out or not? And then how do you know what kind of shape it is? Well, you got to draw the Lewis structure. So all of this is really, really, really building on it. So make sure that you know that you got the beginning of chapter 6 down and you can recognize how to write and name chemical formulas, and then kind of build yourself up to this point where you can take a Lewis structure and figure out properties of something, right? If it has really high, really strong bonding or intermolecular forces, then it's going to be held together really tightly, so it's going to have high melting points, high boiling points. And that may affect the way the substance looks, that may affect the way the substance behaves in other substances. So you're getting to the point where you know enough chemistry now to kind of predict the way something will behave based on what you know, which is super cool. So here's a nice little diagram that the textbook gives us, table 6.18, giving us the strength of these attractive forces. Note that covalent bonds themselves are a lot weaker than ionic bonds. We can think about that too. If you heat up sugar, covalent, it melts. But if you heat up like salt, it doesn't melt. So that's something you kind of can remember about the strength of those. Alright, so this is our practice. Identify the main type of attractive forces that are present in these guys. So tell me, is it ionic, dipole, hydrogen bonds, or dispersion forces? So go ahead and pause and do this work, and then we'll come back and do it together. Alright, so hopefully you have already done it. Pause it. If you haven't done it, do it. Don't just watch me. This is a do-it-yourself kind of subject, not just watch somebody else and learn it. You can't watch somebody ride a bike and learn how to ride it, so you gotta do it. Pause it. Okay. Assuming you've paused it and you got some work to check, we're going to go through. I'm going to draw some quick Lewis structures for these guys. So N likes to have 3 bonds. So I'm just going to kind of draw with 3 bonds. You can check it if you want to. Of course, it might have taken you a lot longer than it took me to do this. I can tell this is going to be polar because I have a lone pair of electrons right here on the center atom. What shape is this? This is going to be trigonal pyramidal. You'll notice that happens with a lot of nitrogens. Trigonal pyramidal. Is it going to be ionic? No, because it's obviously covalent, no metals, so no, not ionic. This is going to be dipole. Because it's polar, but it doesn't have hydrogen, so no hydrogen bonding. So this is going to be dipole. Alright, so for water. Water is this Lewis structure. It's bent and it's superpolar. Water has hydrogen bonding. See how I have a hydrogen bonded to an N, O, or an H? I have a hydrogen bonded to an O right here, so I'm going to have hydrogen bonding. That's going to be super strong. Alright, so bromine, that's what you would call this. You don't call it dibromine or anything. This is just regular bromine because bromine, remember, is diatomic. So bromine is just a couple of bromines hanging out. They're sharing equally because they're sharing with it themselves. So this is nonpolar. So if it's nonpolar, it can only be dispersion forces. Okay. Out of these really quick, which would have the highest boiling point? Here would be our highest boiling point, and this would be our lowest boiling point out of the three that we already have. Okay. So out of these three. Alright, so next, KCl. This is ionic. See how I have this metal? So I'm not going to draw a Lewis structure per se. I'm going to draw this kind of ionic structure. If you want to look at it, that's how you would do it. Don't ever put a line between a metal and a nonmetal because they don't share. This gets transferred. So this is ionic. It's not London dispersion, anything. It's just ionic. So you don't have to say anything about that. Okay, NH3. I got my N. This is ammonia. This is polar. And it is trigonal pyramidal, like most nitrogen structures are. And then I got this special hydrogen bonding here. You see I have an H bonded to an N. That's one of the ones I can have hydrogen bonding for. Now, water actually has stronger hydrogen bonding, but that's like a more advanced topic as to why. But you shouldn't have to choose between two hydrogen bonds, which one is stronger. Okay, so that's your little practice. This should get you through all of study assignments 7 and 8. Use the chart to tell me the shape names. You don't have to memorize those, so use that chart. You're going to get it on your green sheet, so use your green sheet while you're doing your study assignment. All right, last thing. So here's an example in real life of this is an amino acid. You'd be familiar with this if you've taken biochemistry or maybe even just biology. I'm not sure how much chemistry your biology class would have in it. But amino acids have ammonium groups. You see we got some good hydrogen bonding opportunities here. And then we also have a carboxylate group. So you've got some polarity, some polar sides here. So this whole molecule is superpolar. You have a positive side and a negative side. So it's going to have dipole-dipole forces. It may even get some hydrogen bonding in over here on this side. And then it's got some nonpolar sections in the center as well. So you kind of have a lot of stuff going on. But these are biological compounds, and molecules are usually a lot bigger and more complex than simple inorganic chemistry molecules. See, these amino acids are really important in forming lots of other things. So you can make these long chains of things that that you'll use. This is just kind of showing you some of the interactions between these amino acids to make these bigger chains. And then here is the way that I win arguments with my geneticist husband about which science is more important, chemistry or biology, is that DNA is held together by, look at these guys, you see them? Look at them. Look at these hydrogen bonds. They're great. So DNA is actually held together with hydrogen bonds. So, that all goes back to chemistry, so chemistry is the foundational science. There you go. That's just also all the slides for this. If you've got questions, please let me know. Please text or email me, and I will see you guys on Monday with a completed study assignment 7, study assignment 8, and experiment 5, ready for a quiz. This just over the naming part, so not over any of the Lewis structure parts, just over naming ionic and covalent compounds. Okay, so practice that one more time before Monday. Alright guys, see you later.